morning, children. How are you? Today we will discuss electromagnetic induction. Now, before we start this topic, we discuss what do you mean by magnetic flux. Magnetic flux means total number of magnetic line of force passing normally through this surface. Suppose this is a surface, magnetic line of force passing, denoted B, area A. So flux represented phi. Phi is equal to BA. B means magnetic field, A means surface area. Now magnetic field makes an angle theta with normal, then phi is equal to BA cos theta, यानी component of magnetic field. So it is measured the product of component of magnetic field, normal to surface and surface area, is called magnetic flux. It is a scalar quantity. Flux may be positive or flux may be negative. Now, if theta is 0, phi is equal to BA cos theta, theta is equal to 0, then flux be BA, that is positive. If theta is equal to 180, then phi is equal to BA cos 180, then flux is negative. So flux may be positive, flux may be negative. Now unit of flux, Weber. 1 Weber unit of flux यानी phi Weber, denoted WP. 1 Weber equal to 1 Tesla into 1 meter square. 1 Weber is the flux produce uniform magnetic field act normally over a area 1 meter square is called 1 Weber. 1 Weber equal to 10 to the power 8 Maxwell. So it is clear what is magnetic flux. Total number of magnetic line passing through normally the surface is known as magnetic flux. It is also measured the product of component of magnetic field, normal to surface and surface area, is called magnetic flux. Now next topic, what is EMI? EMI means electromagnetic induction. Electromagnetic induction means the phenomena of production of induced EMF or induced current due to change in magnetic flux or due to change in magnetic field is called EMI. Electromagnetic induction means induced current set up, induced EMF produced due to change in magnetic flux over a closed surface or linked with surface, that is known as EMI, electromagnetic induction. Now we have demonstrated one activity. A coil, this is a coil. This coil is connected galvanometer, a magnet, this is a magnet, magnetic field lines, This is first case. When a magnet placed near the coil. This is a coil. This coil is connected to a galvanometer. When the north pole of our magnet is moved towards the coil, current flow in the coil anti-clockwise. Galvanometer shows deflection. Now second case, suppose this is a coil. This coil is connected galvanometer, a bar magnet. This bar magnet away from the coil, current flowing clockwise, the direction of galvanometer shows opposite. And third one is, suppose this is a coil. This coil is connected galvanometer. This is a bar magnet, NS. No change, यानी bar magnet is at rest. No current flow in the galvanometer. First activity shows when the north pole moved towards the coil, current flow in the circuit. Second, north pole away from the coil, current flow in the circuit, but in opposite direction. Third one, suppose magnet is rest, only simple place near the coil, no current flow in the circuit. This activity shows whenever we change the magnetic field or magnetic flux linked with the closed coil, current flow in the circuit. It means the phenomena of production of induced current or induced EMF set up due to change in magnetic flux. This is EMI. Now, this gives Faraday. Faraday gives us magnitude of induced EMF, but Lenz law gives us direction of induced EMF or induced current. Now we will discuss Faraday law. Faraday gives two laws. First law, whenever the magnetic flux or magnetic field linked with closed coil change, induced current set up, induced EMF set up in it, which lasts so long as flux is changing. This is first law. Second law, the magnitude of induced EMF is directly proportional to the rate of change of magnetic flux. Magnitude of induced EMF directly proportional to the rate of change of magnetic flux. So E is equal to minus d phi by dt. Minus sign indicate due to Lenz law. Due to Lenz law. Suppose this is a bar magnet. This bar will move towards slowly towards the coil. Galvanometer will also give deflection slowly. And suppose the bar magnet move fast towards the coil, galvanometer suddenly deflect. This activity shows the magnitude of induced EMF is directly proportional to rate of change of magnetic flux linked with the coil. This is second law. So Faraday gives two laws, first law and second law. Faraday gives only magnitude of induced EMF, not direction. Lenz law gives direction of induced EMF or induced current. Now we will discuss Lenz law. What is Lenz law? The direction of induced EMF or induced current is such that it opposes the cause when producing it. And it opposes the magnetic flux linked with the coil. So what is the statement of Lenz law? The statement of Lenz law means the direction of induced current or induced EMF is such that it opposes the cause when produced in it. Is called Lenz law. Now in simple way, this is a coil. This coil is connected galvanometer. This is a magnet. In this magnet moves toward the coil. Current flow in the circuit. This is anti-clockwise. Current flowing anti-clockwise. the face of this coil represent north polarity. North and north, so they repel, but we have some work against the force of repulsion. This work is converted in the form of electrical energy as a induced current. Now in second, suppose this is a coil, connected galvanometer, this is a bar magnet, N and S, away from the coil, current flow clockwise, the face of coil represent south polarity. In this case, this is south, this is north, they attract, but we have done some work under the force of attraction. So this work is also converted in the form of electric energy as a induced current. So we can say Lenz's law follow the conservation of energy. Both the way, when the north pole move away towards the coil, north pole away from the coil, some work has to be done under the force of repulsion or attraction. This work is converted in the form of electrical energy as a induced current. This is Lenz's law. This is very important. Okay, thank you very much.